Problem 7. We did this one in class. We have a non-conducting wall that carries charge with a uniform density 8.6 microcoulombs per centimeter squared. What is the electric field 7 centimeters in front of this wall if 7 centimeters is very small compared with the dimensions of the wall? Okay. So we need a big wall if the 7 centimeters is small compared with the dimensions of the wall. So we want a very big wall, and we want to line up our cylinder to go through this wall, okay, and out the other side. So I want 7 centimeters in front of the wall. Okay, so our length there is 7 centimeters in front. Okay. This is a Gauss. I already drew the Gaussian surface, so I know that the flux be equal to E dot dA, which is equal to the amount of charge that we enclosed over epsilon naught. Okay. Part A is asking for the electric field. So we go ahead and we'll look for the electric field. It doesn't mention flux at all, but it does tell me that there is a charge density, so I do know that there is a Q. So we're not going to use flux, we're just going to use these two parts. If I draw a cylinder that's coming out from the wall, this wall is giving off electric field, and this end plate and this end plate will actually be gathering the electric field. That's where our flux is going to go through. So these are the ends that I'm looking for. So if E is constant on both of these ends, which it is because they are parallel to the surface, I can pull it out of the integral. Then if I integrate the total amount of area, this is just the total amount of area that the flux goes through, which is this end and that end. Okay. So this will be 2 pi r squared, whatever we chose for a radius of our circle. Okay? 2 pi r squared, because there's 2 of them, and the area of each one is pi r squared. This will be how much charge is enclosed. Okay, so how much charge is enclosed? Well, for that, it's a 2-dimensional object, so we're going to need sigma. Okay. Sigma here would be the charge that's enclosed over the area that's enclosed. Okay, so for Qn here, we're going to need sigma times that area that we enclosed. Okay, so we'll have sigma. The area that we enclosed was this area. Okay, I'll do it in vertical lines. That's the area that we enclosed. So that's just pi r squared. R would remain the same across this entire cylinder, so that's just pi r squared over epsilon naught. Okay. All right, let's get E by itself. So let's move this 2 pi r squared to the other side. So I have sigma pi r squared over 2 pi r squared epsilon naught. The r squared and the r squared will cancel. The pi and the pi will cancel. And we end up with sigma over 2 epsilon naught. Okay, sigma's the density. Density was given. So which means the electric field should be equal to that density. Do a conversion on that density. Okay, so the 8.6 times 10 to the negative 6 coulombs per centimeter squared needs to be converted into meters squared. I will leave this part up to you to get that density correct. The density there, though, should come to be 0.086, and this would be coulombs per meter squared. That's the units for the density. That will get divided by 2 times 8.85 times 10 to the negative 12th, epsilon naught. If that's correct, that's how we should get around our 4.86 times 10 to the 9th newtons per coulomb. It's an electric field. Okay, so there we've got our electric field. That's part A. Part B. Does your result change as the distance from the wall varies? So now instead of being 7 centimeters away, let's make it bigger. Okay, as long as the 7 centimeters is small compared to the dimensions of the wall. So instead of 7, let's make it 10. Okay. This is the electric field, or even better yet, here's the electric field is sigma over 2 epsilon naught. Distance never played a part in here. It actually got canceled out for our radius, but never in here did the distance from the wall matter. Okay? So changing this from 7 to 10 doesn't make any difference. So no, this particular E field is not dependent on any distance. You can go closer to the wall, you can go farther from the wall, and the electric field remains the same. Okay? As long as the area that you're looking at, the distance here that you're looking at, is small compared to the entire distance overall, the entire area of the wall. So B says no, it is not dependent on distance at all because it wasn't in our equation at all.